Good afternoon. I'm Francesco, again, for who was here before. So, we're going to talk about RAG, Retrieval-Augmented Generation. Specifically, we try to see how and when it makes sense to build an agentic RAG pipeline. But first thing first, what is RAG? RAG stands for Retrieval-Augmented Generation, and it's essentially a pipeline made of 3 blocks plus 1, so 4 at the end. Retrieve, augment, and generate, but first ingest. RAG combines 2 different powerful AI, generative AI mostly, techniques. The first one is the retrieval capability, and I say that it's generative AI because it mostly uses embeddings, and embeddings are the first step of a language model. And then the generation. This is easier because it usually involves a language model to generate answers based on the retrieved data and, if we want, the inner knowledge of the language model itself. So in essence, step 1, the input query is given to a retriever. The retriever finds the most relevant pieces. And then, step 2, the retrieved information is combined with a language model to generate a coherent and hopefully context-aware response. One point, the retrieval step does not need to be based on embeddings. It could be based on simpler or more complex, depending on from the perspective, techniques. So it could be a keyword-based approach, could be a BM25 approach, which leverages TF-IDF, term frequency, inverse document frequency. Those are basically information retrieval techniques. But mostly embeddings are used for this step here. This is how a sample prompt for RAG would look like. So your enterprise AI assistant answered the question based only on the following context, if it's helpful. And when I say only, depending on what we want, do we want the model to leverage its own inner knowledge, or we just want the answer to be based on the retrieved context? First question. If you don't know the L, and then we pass the context, the variable there, context. If you don't know the answer, just say you don't know, blah, blah, blah. Then the final prompt is the system 1, the history. At some point, we'll need history. Most of the basic toy demo are without history, but we need history, of course. And then the real question from the user. Question or request. A toy demo. We load some PDF, could be a big one, should be a big one, because if it's a short one, we don't even need RAG at all. One step back. We need RAG because the context windows is limited. Even 1 million tokens for enterprises contexts, it's too small. We need RAG because usually LLMs still have the lost in the middle problem. So they take care to the entire context window, but of course, as a human would do, they cannot remember everything. And usually, what is in the middle is lost. So it's a known problem, lost in the middle. Then we could say, okay, let's fine-tune something. And fine-tuning sometimes it's good choice, depending on how much the knowledge base, the document knowledge base changes. Because if it changes often, then fine-tuning can be expensive, it can be a long task. And while ideally we would want to be able to answer based on new documents almost at the same time those new documents are ingested. So this is a toy demo, long PDF. We load the PDF, we chunk, we split the PDF. This is done again for context reasons. And even for accuracy reasons, we don't want to pass useless information to the model. Even if it's a big one, it doesn't make much difference. When you're working locally, the chunking is crucial. With bigger models, it is still relevant for high level of accuracies, but it's not as relevant, it's not as important as it would be with small local models. Then we store those chunks in a vector store. Remember the embedding part before. We get a prompt. We define a function to format documents retrieved on the vector store. And we finally define the chain. So the context variable is filled by the retriever. Then we format those documents. And retriever plus formatting fills the context variable. We get a question from the user. Then we pass those variables in the prompt. We call the LLM, and we apply some parsing rule at the end. So we don't want the full message to be returned, but just the string, the inner content of the message. Fine. Is it really working? Of course, the answer is no, because otherwise I wouldn't be talking about this today. So no, it doesn't work. I mean, it works, but with some limitations. First, one of my favorite. What if the question itself is a follow-up question? I've seen applications in production even without addressing this big one. So the point is, what if the user asks the first question, and then the first question would be something like, who was the main character of Titanic? So it goes, the whole pipeline goes to the retriever, it gets the information, and fine, the first turn is fine. Then the user, second question, the user then asks, okay, and who are other, what about other relevant characters in the movie? At this point, the question itself doesn't make much sense, because if my database contains more than one movie, we would be considering this code here, we would go on the retriever just looking for what about other relevant characters in the movie. We're not specifying which movie. So if the database contains more than one movie, it would find a lot of results mostly completely irrelevant. So somehow we should condense the whole history, and the last question, of course, into one meaningful query on the vector store. What if the user needs verbatim citations? What if the user question is somehow misleading? This one is crucial. Okay, we can involve a condenser. So we condense the whole history and the last user query into one question to go on the retriever. But we should consider somehow that the way the user phrases his question could be significantly different from the way the knowledge base is written. Usually, users ask questions in an interrogative form, while documents are mostly assertive. Embeddings works good with those kind of differences, but especially for technical knowledge bases, this is still a big difference. If the user asks something in a non-technical language, interrogative form, and non-technical form, while the knowledge base is assertive and very technical, the condensing step wouldn't help much. So we will need to involve a smart condenser. So not just condensing the whole history into one standalone query, but also enriching the query based on how we stored those documents, the original knowledge base, based on how usually it is written. There are several techniques in this direction. The most intriguing one is called HYDE, and stands for Hypothetical Document Embedding, in which, instead of doing all this stuff, they first do the condension part. And then they ask, just based on a few example documents, they ask to an external language model to generate an answer to that question. So without going to the vector store, with nothing, we just say to the model, to an external model, hey, I got this question from the user, please answer. We don't care about the answer itself. I mean, we're not relying on the answer itself, but we are relying on the structure of the output. So we will use this fake answer as the query on the original vector store, on our vector store, to search similar documents, which should, we hope, really answering the question. That's a tricky one, but it works very good. More simpler solution would be just involving a chain which breaks down the question of the user if needed, if the question is a complex one. Which can be, it's usually called step-back prompting, or least to most prompting. We split the original question in a smaller, and we hope easier, questions before going on the vector store, and then we go on the vector store with all those questions, with all those queries. Okay, the first three are pretty easy to solve, at least conceptually. But then we should consider a few more problems. So what if the LLM doesn't really answer the question? We should check for some kind of consistency before returning the user with the answer. What about the hallucinations? We didn't even mention this one. And given the toy demo, I have no idea where to put a check for hallucinations. What about privacy issues? So what if we don't want the model to see the data? How can we work with privacy constraints in a GDPR-like environment? But my favorite one is if someone asks for a meta question. So how many questions, the canonical example is, how many questions have I asked you until now? It's a very complex question. Why? It's an easy question, but it would go on the vector store looking for the solution, which of course makes no sense, because the answer itself, the question itself, it's not a proper question. We don't need to go on the vector store searching for how many questions the user just asked. The model just needs to provide an answer, a direct answer, simple one. So going on a vector store, we have two drawbacks. The first one is we're wasting tokens times latency, and then most likely with small model for sure we won't get the right answer. But even questions like, are you sure? I mean, we don't really need to go again on the vector store for those kind of questions. We just need to check based on what we have retrieved in the last iteration on the vector store and the answer generated. We just need to check the answer, but we don't need the full pipeline to run again. A few points on the simple mitigations. So for the what if the user question is misleading, we can work on the ingestion step and the retrieval step. In ingestion step, we should apply better, more sophisticated chunking strategies. Semantic chunking is very intriguing. Unfortunately, it doesn't work in real life. Semantic chunking is when you split the chunks not just on a number of tokens or characters or separators, but when the meaning of the sentences diverges. So if we change the main topic of our discussion in a document, we should split the chunk there when we change the topic. Unfortunately, it doesn't work in real life. It's a very good idea, clever idea, but doesn't work. We tested it in all possible kind of scenarios. It's a great idea, but doesn't work. Embeddings are not that good, splitting chunks just with the similarity score. So we should do something more sophisticated, more expensive. Not sophisticated, but expensive, like agentic chunking or contextual chunking. So we have two options. Agentic chunking, the simple agentic chunking, it just involves an LLM or an SLM, small language model, to chunk the original document. So we pass the documents and say, please split this document. Make some relevant chunks from this document. While context chunking is more sophisticated, the original idea comes from Anthropic. So we split the chunks in whatever way we like, based by characters, tokens, whatever. But then we ask a language model to, we pass the original document and the chunk itself to a language model, and we ask, please give me all the relevant context for this small chunk within this big document. Why we're doing that? We're doing this because the problem with chunking is the loss of contextual information. The classical canonical example is financial reports. At the end of the financial reports, we say, okay, the last year, the total revenue was increased by 15%. Okay, but what was the original amount? Of course, if we do regular chunking, we wouldn't know that. The chunk would not contain the information, no matter how much we make pressure on the language model, the chunk itself doesn't contain the information. But if we pass the entire document, the entire financial report, and the chunk asking to extract from the long document all the relevant contextual information to ground the chunk, then we would have the chunk plus all the contextual information. And for sure, with this kind of chunks, we would have the original revenue before the plus 15% at the end of the year. So answering a question based on that chunk would have all the relevant and needed information. Then the retrieval step, we already we already went through those ones. So condensing history and last questions into standalone query, rewarding and trying to vary the user's query. What if the user needs verbatim citations? This is a bit slightly more complex, which we need to involve to give an explicit ID or reference to each context document. And we should try to leverage function calling LLM abilities to extract not only the answer to the question, but also in a structured way, leveraging structured output or function calling, the relevant verbatim citations, the passages used to answer the question. Important point here. Usually, when we say we're giving citations to the user, we just tell the user what documents we used and what documents we retrieved from the vector store. But it's not the same thing. We might retrieve documents from the vector store, but actually not using those information to answer the question. So in this case here, we would directly need the help of the LLM. So together with the answer generation, we need also the LLM to tell us what parts of what passages it used to generate the answer. As I said, those mitigations are not enough in real world because there are a number of points which are not addressed by the mitigations, which cannot be addressed in that way. So agentic RAG comes into play exactly for this reason. An agent is an LLM integrated with specific tools. Once more, I said this before in the session this morning. An LLM itself does not call any tool. It doesn't execute any code. It just tells us what are the tools that we need to call. And then we, with our tool executor, in a tool executor environment, we execute the code, the tool, and pass back the result to LLMs. LLMs are, at the end of the day, text generators, text or audio, whatever generators. They cannot run any code. They can write code, and they can get feedback from the executed code, but by themselves, they cannot execute anything. Agents are LLMs plus tools executor. So they can they are equipped with our code to execute tools and get back results. So an agent uses tools to fetch data, to interact with APIs, to manipulate external systems, and it has autonomy to perform tasks based on the context and, of course, the system instructions. It can somehow reason, and it definitely can use external information to make decisions or taking actions. So while in traditional RAG, each step follows a fixed path, so retrieve, augment, and then generate, in an agentic RAG pipeline, the flow is definitely more dynamic and flexible. So the agent decides what tool to use and when, with some level of freedom. And it can engage in a multi-step process. So it can make decisions based on the context. In fact, instead of a linear flow, those agents can interact with external systems and can adapt to changing information. Sorry. And the ability itself comes from the tool calling capability of the LLM. So they have an autonomy, they have some freedom because they can call tools. But the challenge is to determine how much freedom we should give to any agent, specifically to RAG agents. Because without a specific predetermined flow, agent can overuse tools, can misuse tools, and this leads to costs, inefficiencies, and low accuracy. On the other hand, if we force a strictly rigid path, well, we are actually eliminating all the flexibility, and so it's no different from a structured system like the toy demo, more complex than the toy demo, but still a very structured system. So the goal is to strike a balance. We should allow agents to adapt, but still ensure efficiency and reliability. So state machines are usually the answer, and I say usual because of course it depends on business use case. But state machines allow us to define clear steps and transitions between different agents' decision. And the transitions define how the agents move from one task to another one. This is how a state machine, a simple one, would look like. So from the input, we go on the retriever, we grade the documents we got from the retrieval step. Then we ask to a model if the documents are relevant or not. If those documents are not relevant, we're also asking for some feedback so we can rewrite the question and go again on the vector store or wherever we want to retrieve again new documents. If the documents are relevant, then we generate an answer. And again, we ask to a separate language model if the answer is grounded by facts or if it hallucinates. If it hallucinates, we will ask for more feedback and we will go again to the generate step saying, hey, please, you generated this answer, but the answer seems to be hallucinating for this reason, with the feedback from that model there. Once we're satisfied, we pass we go directly to the final step, and the final step is asking to an external language model if the answer answers the question. So not just if it's grounded, but if it actually answers the original query. Again, if the answer, if it doesn't answer, we'll start from rewrite question, and then again on the retrieve vector store. Usually, we want to save some money, and we try to use small language models for specific, simple, small tasks, like, are these documents relevant? Yes, no. If no, give me some feedback. It's an easy task, simple, easy, condensed task, so we can just leverage the ability and capabilities of small language models. Same for hallucinations, and the final check if the answer answers the question with small language models can be tricky. At the end of the day, what is called what's usually called conditional edge, are documents relevant? Is this answer hallucinating? Is this answer answering these questions? Those are usually called conditional nodes because based on the response we are getting, and the response we're getting from language models, or we can also leverage some standard canonical checks, like is the answer short or long enough, just counting the words? Based on that, we apply some decision and we change the path. And those conditional edges, at the end of the day, in a Python way, this is lang graph, but it would be the same with semantic kernel in C# or other frameworks in whatever language you like. It would be more or less the same. So we're essentially asking and using structured output. So we're leveraging a prompt asking for hallucination checks, grounding check, or coherence check, whatever we need to check, and we are leveraging function calling to get a structured response. Based on the response, which is structured, so we can apply the normal traditional software logic. If in this way, then do this, otherwise do that. This is a more complex agentic RAG pipeline. From the input, key points, anonymization here, condensation, because in the other flow we were not considering condensation. Here we're considering condensation. Task router, so we can address meta questions. The task router should decide if the question needs some external tool or if it's just a general conversation and then directly generating the output. We have more than one knowledge base. We have the vector store. We have DB search with a text to SQL maybe. We have web search. And then the final part is more or less the same. One point to consider here is that even general question goes through hallucinations check and the final check, so the answer is answering the question yes or no. And then we have the de-anonymization at the end. Whether the general question should pass through hallucination and coherence check is up to you and up to the business case scenario. This is more or less production ready. But still, one question you should ask is, how do we handle follow-ups? Okay, we are considering here the condensation, but for every follow-up, we need, follow-ups, are they only general question or contextual question? What about something in the middle? Where is the autonomy of the agent itself? And this is one point. The other one, so what's beyond, why the schema, why that flow is not really already production ready? Because we need to involve at some point maybe text to SQL or maybe graph RAG for some kind of knowledge basis. For the first one, so the autonomy of the agent, and so the capability to handle any kind of follow-up questions, a real-world agent might look like this. So it seems this is a completely autonomous agent. So we are giving the atomic operations to the LLM. But of course, you might object that it's too simple. Yes, you're right. So this is a real-world example. So not just giving the plain atomic operations to the model, but encapsulating the autonomous agent within a structured framework. So the input needs the anonymization step. Then we have the autonomous agent, so LLM with tools and tool executor. At the end, before returning the output, we have some sort of guardrails, so hallucination check, relevancy check, coherence check, whatever. And before the final output, we have the de-anonymization step. And the tools, those are not the atomic tools. We usually don't want to give the agent the very basic low-level tools. In fact, the white nodes, DB search, I just realized that red doesn't read really good on black, sorry. But the first white node is DB search through text to SQL, and the second one is plot generation. This is a real-world example from an healthcare application we have in production. And doctors usually need to generate plots based on data. And text to SQL and plot generation, those are complex tools. So those are agents themselves. I'll show you in a second what I mean. And human feedback in the middle, before going to the database or right after querying database, we might want the user to give us some feedback or approval. As I said, the agentic the text to SQL tool is an agentic tool. It's an agent itself, specifically designed for one thing, text to SQL. And it's usually something like these. So from the input, we get the relevant tables. And we get the relevant tables providing models with documentation and few-shot prompting and examples through few-shot prompting. Then we get, once we are fine with the tables, with the relevant tables, we get the schema of those tables and some domain documentation. Then we find pertinent and relevant examples. Again, in this entire pipeline, based on our experience, even when you leverage fine-tuned language models, you need few-shot examples to build properly formatted and, of course, relevant SQL query. Text to SQL is an hard task. So the more dynamic few-shot prompting you can get, the better the results will be. So we get relevant examples. So based on the user, on the input of the user, we find similar queries, human-curated, from a human-curated data set. So we find the relevant similar user couples, user query, and humanly generated SQL. And then we ask the model to generate the query. We try to execute the query, of course, low level, no write permissions, if at all possible, given the business use case, just read permissions. We execute the query, and we check, I mean, if everything is fine, no errors, we just return the output. If errors are raised, then we leverage the stack trace and ask the model to correct the query itself, and again, rerunning the execute step until we're satisfied, and we decide if we want to format the output or pass the raw output from the database to the original model who called this tool. Remember, this is a tool. While for the plot, it was more complex. Again, this is still a real-world example. And we had some troubles managing the plot because it's pretty easy to hide results from a SQL query to the model. We didn't want, in the first stage, we were not using a local model, so we were using a model on the cloud in a very restrictive business scenario, so healthcare. GDPR is so strict there. So the model could never see the data. So how do we generate plots without having the model to see the data? Well, models are good at one thing especially, generating text, of course, and generating code. So we extracted, once we got the result from the database and we needed to generate a plot, we asked the model to generate a couple of functions, Python or whatever, usually Python, it's easier. 2 functions. One, to adapt the schema of the data from the database, so just the schema. The model just sees the schema, not the raw data, just only the schema, the output schema. So we ask it to generate a function to adapt the format for visualization. So the user was asking for a scatter plot. We got a result from the database with this, with a given schema, and we asked the model to generate a function to adapt the schema to the scatter plot schema, the original schema to the scatter plot schema, and then to generate one more function, which is the pyplot or whatever framework you use with the actual plot, but this function had to take into at one parameter the data transformed by the first function. So at the end of the day, we had the output data from the database. We had one function to format data and one function to visualize, to build the plot. We got those functions together and we locally executed the chain of functions to get the final plot. So the model, even with this one, the model never sees the data. It just sees the structure. Graph RAG is the other part. Until now, we have addressed only local questions. What about global questions? So local information are the one that can be stored together from a raw knowledge base. But global questions like how many films are similar to Titanic, that's a global question. It's not local. It's unlikely that you can find that specific answer in the knowledge base. But it's the relationship between the documents in the knowledge base that gives you the answer to this global question. And Graph RAG comes into play to solve this global need. How it works? Well, it works extracting a knowledge graph with an LLM from the entire knowledge base. Of course, 2 attention points are the multi-turn extraction. It's very unlikely that the model extracts all the relationships and entities in just one step, so multi-turn extraction. And be careful about entity and duplicates removal and new entities. So once a new document is inserted in the knowledge base, take care about that process. In fact, when you upload a new document, you should extract the relationships accordingly to the existing knowledge graph, but still staying open to catch new entities and new relationships. Strike this balance is not that easy. And usually, we leverage graph algorithms to build communities. So when we see the nodes in a knowledge graph are connected, highly connected, we consider those nodes as a community. And we ask an LLM to generate a summary based on the single of every node in the community. Again, when you upload a new document, potentially you might need to update all community summaries, because if a document is highly linked, highly connected, then you need to update all the community summaries related to that entity. And at query time, we should understand if the question is local or if the question is global. If the question is local, then we can apply the canonical text-to-embedding approach, so the agentic approach we just seen, or we can implement an hybrid approach. So we leverage both together. We give the autonomous agent an external tool to fetch also the knowledge graph to get information about the relationships of entity, even if it's not strictly needed because the question is somehow local. Or if the question is global, we usually have to involve a map-reduce approach. And so we generate an answer based on each summary, on each community report, potentially linked to the entity involved in the original user query. So we extract the potential linked entity from the user query, and we extract all the community summaries linked to those entities, and with a map-reduce approach, we finally generate a global answer. Yes?
How can you identify if the question is global? So how can you simplify that question?
Usually it's, I mean, in real-world cases, it's pretty easy to have the model to do that for you. Why? Because you give the model some information about the kind of documents you stored on the vector store or whatever. So you tell each of those documents are clinical records, specific clinical records for specific patients. So the model itself will understand with some prompts, just some prompting, that if I ask for a meta-analysis for more than one patient, then most likely it's a global question. But this one is a great point. In fact, in real world, it's almost always an hybrid approach. So giving the access to the graph to the autonomous agent. So the autonomous agent has one more tool to explore the graph. And the graph exploration can also start based on embeddings, because mostly all the graph databases contains also inside natively a vector store. So you can store a node with textual information and embeddings for that textual information. So you can start the search not randomly on the knowledge graph, but starting from the embedding similarity, from the similar nodes. I'm in time. I'm finished. Thank you.